Hey everybody, welcome back. I've got a really cool linear algebra problem I want to share with you. So suppose x, y, and z are real numbers. A is the following symmetric matrix. X plus y plus z is positive. X times y times z is exactly 2. And a squared equals the 3 by 3 identity matrix. Well, under those assumptions, we want to compute x cubed plus y cubed plus z cubed. So I think our first plan of attack is to investigate this, or at least a portion of this. So let's look at a squared. So of course that means a times itself, but as I mentioned, we're just going to look at a portion of that. Okay, and we said that equals the 3 by 3 identity. Okay, so I want to look at, in the product matrix, the upper left entry and then the upper middle entry. That's going to give us at least something to work with. So let's look at this upper left entry. So it should be, well, think about row by column, right? So it should be x squared plus y squared plus z squared. And then let's talk about this upper middle entry. So again, just row by column. So it's going to be xy plus yz plus xz. And then for the other 9 entries, some sort of stuff. I don't need that right now. Okay, so if two matrices are equal, then they're equal component-wise. So this must equal 1, and this equals 0. Let's take note of that. So x squared plus y squared plus z squared equals 1, and xy plus yz plus xz is equal to 0. Okay, so my goal is to get here. I notice we've got some information about this being positive, and we know exactly x squared plus y squared plus z squared is 1. So I'm thinking maybe if we did some long division, maybe this divided by this will bring about an x squared plus y squared plus z squared. Let's see if that's helpful. Okay, so we've got x cubed plus y cubed plus z cubed. That's divided by x plus y plus z. And I'm just going to start off by saying x goes into x cubed, x squared times. Okay, so I'm just going to distribute and then subtract. So that's going to give me x cubed, but I subtract. That's going to give me yx squared or x squared y, but I subtract. That's going to give me x squared z, or zx squared, but I subtract. Okay, let's see what we still have. We still have this y cubed minus yx squared minus zx squared plus z cubed. Okay, so thinking about this, so let's do minus yx. Okay, so if I multiply here, that's going to be minus yx squared, but plus. That seems nice. And then minus y squared x, but plus. And then minus xyz, but plus. Okay, so let's see what we have left. So we still have this y cubed. Those canceled nicely. I still have minus zx squared plus y squared x plus z cubed plus x, y, z. Okay, maybe we can take care of this. And so plus y squared. I'll distribute. When I distribute to the second term, that'll take care of that, so I'm not too worried about that. So if I distribute, that's going to be x, y squared, but minus when I subtract. When I distribute here, that's going to be y cubed, but minus when I subtract. And that'll be z y squared, but minus when I subtract. Okay, so what's left over? Let's see what we have here. Okay, so maybe minus zx here to help with this. And so when I distribute here, that'll be zx squared. That's minus, but when I subtract that, it'll be plus. So here, this will be minus xyz, but when I subtract, plus. And this will be minus z squared x, but when I subtract, that'll be plus. Okay, so let's take care of this now. So how about plus z squared? And again, just distribute and subtract. So this will be xz squared, but minus when I subtract. This will be z squared y, but minus when I subtract. This will be z cubed, but minus when I subtract. Okay, so this seems promising. So this is 2y squared. No, that's a z, isn't it? It's the trouble with the z's and the 2's. There we go. zy squared minus z squared y plus 2xyz. There we go. And then let's do minus zy to help with those. There we go. So distribute and then subtract. So that'll be plus another xyz. So that'll be plus when I subtract, right? So this is going to be y squared z, or zy squared. And then here this will be z squared y, and then plus once I subtract the negative. And it looks like I've got this remainder of 3x, y, z. Okay, so from this, what do we know? We know that this divided by this is equal to this plus the remainder, right? So maybe I'll say that. So we'll say that so this is equal to x plus y plus z. I'll write this with all the squares together because we do have, if you think about it, we've got a statement about x squared plus y squared plus z squared from before. So that's why I considered such a division. I was hoping it would bring forth x squared plus y squared plus z squared, and it did. And then minus, I can just factor out that minus, right? So that'll be xy plus yz plus xz, which seems handy, plus our remainder. Okay, that seems pretty nice because if you think about what we had before, we know that this is equal to 1. We know that this is equal to 0. We know from our assumption that this is 2. This is the only part we don't know anything about, right? So if we can find a replacement for that, we're doing pretty well. So let's work on that next. So we're fine here, here, and here. Let's find a replacement for this. Okay, let's make an observation. Okay, so let's square this and see what happens. Again, we're trying to figure out what this is. That should be x plus y plus z quantity squared. I group it like that because I tend to square my binomials using the binomial expansion. And if I think about a trinomial like this, it's pretty nice. Okay, so that'll be the first object squared plus 2 times the product plus the last object squared. And we just continue in this way. So again, just applying that again. So that's x squared plus 2xy plus y squared. Let's distribute 2z at the same time. Okay, so that seems pretty good. And then if we group things together in a clever way, we can use some of what we know from before. So it looks like we've got an x squared plus y squared plus z squared plus 2 times xy plus xz plus yz. Okay, but we know what this is from before, that's 1. And we know that this is exactly 0. And so if this squared is 1, then x plus y plus z must be 1. Essentially, that solves the problem, so all we have to do is go back and substitute. So again, from our long division, we had this. Okay, so we said this was 1. We also said that this was 1 from before. So this looks like 0. And this, from our assumption, was 2. And so it looks like x cubed plus y cubed plus z cubed is exactly 7.